Hey guys, it is last chapter 1212. This is chapter 20. Again, I've updated the PowerPoint in the share class files, so if you want the latest version to follow along with, that's where you need to go to find it. This is all about electrochemistry. It will require us to remember some things from 1211, specifically chapter 4 is when we introduce oxidation reduction reactions. All of this chapter is built off of the concepts of oxidation reduction, but we're going to go a lot further than we did at that point. So we have to review what is oxidation and what is reduction. So we learned the term in 1211, oil rig. Oil is for oxidation, is losing, OIL. Oxidation refers to the losing of electrons by an element. Reduction, so that's the rig part. Reduction is gaining electrons. We recognize whether an element is gaining or losing electrons by looking at what we either call the charge or the oxidation number. Okay, oxidation number is just what we call the charge when we have a covalent compound instead of an ionic compound. It's pretty much the same thing. It's just a detail between the two. So, how do we know whether it's changing? Well, essentially, we have to look at a reaction, and we have to assign all the charges to all the elements on the left side of the reaction, which are the reactants. And then we go back and assign all the charges of the same elements on the product side, and we're going to look to see which elements are changing from left to right. If the charge is going up, that's going to be oxidation, because when you lose electrons, that's going to make the charge increase. If you have an element where the oxidation number goes down, that means it's gaining electrons, that's going to be reduction. So those are the things we're looking at when we assign these things. And then we also want to be able to look at the reaction and say, okay, what compound is being added to this mixture that's causing the oxidation? So that's called an oxidizing agent. Some compounds are really good at making other compounds get oxidized. We also can have compounds that are useful for reducing things. So whatever we're adding that's going to cause the reduction to occur is called the reducing agent. We'll deal with that in just a minute. So what we're going to do in the reactions that I have listed, we're going to assign what element's being oxidized, what element's being reduced, what's the oxidizing agent, and what's the reducing agent in each of these. Now to do it, we have to assign charges. So I have to kind of go through and remember my rules. Anytime I have an element in its pure form, if it doesn't have a charge labeled, like this is Na is just regular sodium metal. If it's in its normal elemental form and there's no charge, that means the charge is 0. So the oxidation number of sodium in this case is 0. This is elemental oxygen. Its charge is also 0. But when I put them together, they react. When I form this compound, the sodium is now going to have a +1 charge. The oxygen is going to have a -2 charge. So if I look at the overall process, sodium went from an initial charge of 0 to a final charge of +1. Its charge went up as I moved to the right. That if the charge goes up, that means it lost electrons. Sodium was oxidized. The element sodium was oxidized in this reaction. The oxygen went from 0 to -2. So the element oxygen was reduced in this reaction. Okay, so that's assigning what element's being oxidized and reduced. Then I would look at it and say, okay, well, what was added to cause the oxidation to occur? We already said that sodium was oxidized. So what did we add to cause it to be oxidized? Well, it's the other compound. And usually when I'm saying the oxidizing agent is the whole compound, so I would say that O2 is the oxidizing agent. The whole compound is labeled as the oxidizing agent. On the other hand, we said the oxygen got reduced. So what caused that reduction to occur? Well, what did we add? We added sodium metal. Okay, so in this case, sodium is being oxidized, and sodium is also the reducing agent. Next compound, next reaction. We look at this one. I can assign my charges. Hydrogen's +1, chlorine is -1. Elemental iron is going to be 0. Over here, I know chlorine is -1, which means the iron has to be +2, because it has to be a neutral compound, so the charges have to cancel. And then the hydrogen in its elemental form will be 0. So if I know all those charges, write them all down, I would notice that hydrogen is going from +1 to 0. +1 to 0, that's a decrease in charge. Hydrogen's being reduced. Chlorine was -1 here. When I came over here, it was still -1. So chlorine is actually a spectator in this reaction. It's partnering up with different elements, but its charge never changed. So chlorine did not accept or lose any electrons in this reaction. And then iron went from 0 to +2. If the charge of iron went from 0 to +2, that's an increase in the charge, so iron was oxidized. So we had hydrogen getting reduced, we have iron getting oxidized, chlorine is a spectator. Then we might ask, what is the oxidizing agent? Well, we already said that iron is being oxidized. What compound did we add to cause iron to be oxidized? HCl, hydrochloric acid. So again, the whole compound is the oxidizing agent. Then we say, okay, well, hydrogen got reduced. What did we add to cause that reduction? Iron. Iron is my reducing agent. Okay, so that's it for that one. Next one, we get a little bit harder. Some of these reactions become more challenging as you move on. I'm not sure how well it shows in the slide. It's Fe+2 plus the permanganate ion, Mno4- yields Fe+3 plus Mn+2. So when I look at these, I have to be able to assign my charges. Again, review 1211 if you have trouble with this. The iron initially, it's an element and it has a +2 charge beside it, so the oxidation number of iron is obviously +2. When I look at permanganate, this one's a little bit harder. Oxygen, if it's the most electronegative element present, an element that's electronegative is going to always take its normal negative charge if it can. So each oxygen, they always like to be -2. So the oxidation number of each oxygen atom is -2. Together, since there are 4 of them, they contribute a total charge of -8. But if I ask you the oxidation number of oxygen, it is -2 here. Okay? But since there are 4 of them, -2 times 4 gives me a -8. The manganese has to be a +7, because if I add +7 and -8, that gives me my overall charge. I know the permanganate ion, the sum of all the charges, has to equal -1. Okay? So, manganese is +7, oxygen is -2. Then I go to the other side, iron's +3, manganese is +2. If you're wondering what happened to the oxygen, when we start balancing these equations, what's going to happen is sometimes the oxygens are going to be freed up from the compound and actually just join the aqueous solution, become water molecules or hydroxides or something like that. If that happens, then typically that means that the oxygen was not one of the main players in the reaction. It's not being oxidized or reduced, so we don't need to worry about it too much. Okay, so I have enough information here. I can see iron goes from +2 to +3, charge goes up, that's oxidation. Manganese is going from +7 to +2, its charge goes down, it's reduction. If you ever look at a reaction and find that both elements are being oxidized or both elements are being reduced, you probably made a mistake. It's kind of like playing poker. If one person wins money, leaves with more money than they came with, that means that somebody else has to leave with less money. There's an exchange going on, and you have to conserve. In a poker game, there's a certain amount of money at the table, and it all has to balance out at the end. In a reaction, there's a certain number of electrons present, and you can't have any electrons appear or disappear during the reaction. You have to balance the atoms. We also have to balance the electrons. That's key. So, if you have trouble with your rules, just remember pure elements have a charge of 0. Oxygen is -2 pretty much all the time, unless you put it with fluorine. Fluorine is the only element that's more electronegative than oxygen. So if you put fluorine with oxygen, fluorine will get its normal negative charge, and you'll actually have oxygen be positive in that case. but that's unusual. Hydrogen is almost always +1 unless you put it with a metal. There are cases where the hydrogen, since it's a non-metal, it could have a negative charge and a metal could have a positive charge, but again, that's kind of unusual. Fluorine's always -1. Now these charges all apply unless they're pure elements, which then I go back to the first rule, where pure elements always have a charge of 0. Now oxygen can also exist in a peroxide and have a -1 charge, but again, if you had a compound that was a peroxide, you would probably know it. It's in the name of the compound. When you look at the compound, the more electronegative element almost always gets its normal negative charge. For instance, oxygen is almost always going to be -2. When we look at a neutral compound or polyatomic ion, we know that the charges have to add up to the overall charge. So if I have a neutral compound, I know that all the charges of the atoms in the compound have to add up to 0. If I have a polyatomic ion, all the charges have to add up to the overall charge of the polyatomic ion. So on the previous slide, when I had permanganate, which was MnO4, the overall charge is -1. So that tells me that the charge of all the atoms in the group have to add up to a -1 overall charge. So just for practice, we can do a couple of these. I have the NO2 molecule. NO2, the more electronegative element is oxygen. So it's going to get its normal -2 charge. So both oxygens are going to be -2. Cumulatively, that means that the oxygens are contributing a total -4. This is a neutral compound, so that means that nitrogen has to be +4. Now nitrogen doesn't want to be positive. Nitrogen is a non-metal. It likes to be -3. Oxygen likes to be -2. Well, they can't both be negative. Who gets to be negative? It's always going to be the more electronegative one. Okay, so in each of these compounds, the oxygen is going to be negative because it's the most electronegative element present. That means nitrogen has to be a positive. So in the first one, I get -2 and +4 are the charges for NO2. If I look at nitrate, again, the oxygen's going to be -2. There's 3 of them, so that gives me an overall charge of -6 from oxygen. There's a -1 charge overall, so that means that out of the 6 negatives with the oxygens, I need to cancel out 5 of them through the nitrogen, so that when I add them all together, I have a -1 charge. So the oxygens are -2 each, the nitrogen's a +5. If I add them all together, it gives me a -1. N2, that's the elemental form of nitrogen. In that case, the charge of nitrogen is 0. And then NH3 is kind of a weird compound. It's written backwards, but if I look at electronegativity, nitrogen is more electronegative than hydrogen. So nitrogen is going to get its normal negative charge, which nitrogen likes to be -3. That means that each hydrogen has to be a +1. That gives me a neutral compound, which is what I would have expected, because hydrogen is always +1, nitrogen likes to be -3. Most of the time these charges will work out and it should make sense, but you do have to practice. Okay, so when we have a redox reaction, there are several different ways we can do this, okay? So first of all, an example, if I take a piece of zinc metal and stick it down into a solution that contains copper sulfate, what can happen then is a single replacement reaction. Single replacement reactions are almost always going to be redox reactions. And what happens is the zinc, when it goes in there, most metals want to have a positive charge. So the better zinc is at giving its electrons away, which that means it's a reducing agent. Because if it gives its electrons away to another element, it's going to reduce the charge of the other element. So zinc is a pretty good reducing agent. It's good at giving its electrons to other metals. So zinc gives its electrons to copper. When the zinc becomes charged, that allows it to dissolve in the solution. The copper ions that are floating around the solution, once they accept the electrons from the zinc, the copper atoms become neutral, and at that point they're not soluble anymore. So what happens is they switch places. On the surface of the metal, every time a copper atom touches the metal, the zinc is going to shove off 2 electrons. Zinc is to swim away in the solution, and copper deposits out of the solution. So that's what I see over here. is that over time, the copper comes out of the solution. So if you can see the colors, the blue color of the solution is starting to disappear as copper comes out of solution. The copper is going to form on the surface of the zinc. So I kind of have a dark red material that forms. That's the copper metal, although it kind of forms in a powdery form. Some of it even falls to the bottom. And the solution becomes less blue because the copper is all coming out. If you took the piece of zinc and weighed the piece of zinc, if I scraped the copper off, what you would also find is that the piece of zinc should be getting lighter because some of it is dissolving away into the solution. If you put a small piece of zinc in a solution, if it had enough copper, the zinc should actually fully dissolve into the solution as copper comes out. So, this reaction, we have a redox reaction going on in one container here. Again, that when we move into batteries and galvanic cells, that's going to be a little bit different. But I have a direct transfer of electrons. When the copper ions in solution come in contact with the zinc gives 2 electrons from each zinc atom to each copper atom. There's an exchange of 2 electrons that occurs. That's the redox. Zinc is giving electrons away, so zinc is being oxidized. Copper is accepting the electrons, so it's being reduced. It's all happening in one container, so this is what I would call an electrochemical cell where a reduction-oxidation reaction is occurring. Now, when we want to actually harness this and do work with it, we're actually going to split these reactions into 2 separate containers, and the electrons are going to flow through a wire. That's traditionally what we're going to refer to as an electrochemical cell. We're going to have 2 half cells that we're going to do. I'm going to cut off the video for now. We're going to pick that up in video number 2.